A little background about me and this work. I started this when I was a sophomore in undergrad, just kind of learning CFD, and my principal investigator sticks me on flow passive cylinder as a fundamental study. So this has nothing to do with biology, but I am still in this session, so we're going to be learning about more flow passive cylinder today. So overview, I'm going to go over the problem statement. So the motivation, basically, since it was like my first analysis, was to just find a gap in the literature associated with flow passive cylinder. So I'll be going over that problem and then go through my methodology, some verification and validation, and present my results. So the problem statement, what are we answering? I figured out that while there was investigation into tandem cylinders, as we see, where there's one cylinder and then another cylinder straight behind it, and there is investigation with sidewalls, there is not really investigation with multiple cylinders confined to sidewalls. We can imagine this two-cylinder situation as the fundamental geometry inside of heat exchangers, because we have tubes and they're close together, and there are sidewalls close together, and so this is a good fundamental area to investigate, and should have hopefully some impact. So I guess I can, how do I go back? The Straw-Hall number is the flipping from the lift coefficient. So the lift coefficient goes up and positive, and then it goes negative, and the frequency of that oscillation is the Straw-Hall number, or the non-dimensional frequency. So my methodology is to build a verified and validated model based on simpler cases so that I can build confidence that I am simulating the physics correctly. So the first example is this single unconfined circular cylinder. Very simple Reynolds number, straight out of the textbook. I'm sure we all know flow passive cylinder. And the second example, again, as I mentioned earlier, is we're just slapping another cylinder behind it. The Reynolds number does not change in definition, but when we add a confining sidewall, the Reynolds number definition changes. And in the literature for flow passive confined flow passive cylinders, this U center line sometimes is U average. And so to compare the results, some adjustment to your Reynolds number might be necessary depending on what the paper you're looking at uses as their characteristic velocity. So we have a parabolic inlet profile that's just the standard parabolic inlet profile for fully developed flow. Since I don't want to simulate a massive geometry and have some inconsistencies in how developed is it when it hits the cylinder, I want it to be consistent, and so that's how I specify that. Another important thing for the study is a blockage ratio. So how much of the channel is the cylinder taking up? Is it blocking the channel or not? That's the blockage ratio. So tandem confined cylinders, this is what we're looking at today. Reynolds number is 150. Because there was one experimental study that looked at this, they didn't collect any data experimentally for the force coefficients, but they still had some flow field comparisons. So if we look at my mesh generation, it's a very simple mesh because it's a very simple geometry. If you look at the unconfined flow, we see this polar region around the cylinder, so we can have good orthogonality in our cells, and the cell size here is selected such that the boundary layer at this Reynolds number is fully captured, and we're not losing any of those physics, because the boundary layer formation around the cylinder is actually very important in determining the force coefficients for the cylinder, not so much the Straw-Hall number, but either way, this the distance, the size of this cell closest to the cylinder was kept fixed for all of my simulations, since they're all in the same Reynolds number range. And yeah, so this is how I expand the domain out. The cells are really big at the ends because they don't need to be small, because nothing is happening there. If we look at when I have sidewalls, the mesh becomes less efficient. I would like to see coarser cells near the inlet. I don't think the inlet, since it's a parabolic velocity profile, nothing's really changing there. It doesn't need to be this refined, but the software that I was using to mesh, ANSYS iSim CFD, I couldn't figure out really the best way to get it there, so this is the best that I could do with that tool. So as far as model development, I decided to plug these meshes into OpenFOAM because it's a simple problem. I didn't need to understand much about OpenFOAM to be able to do this, so that was good. Using low Reynolds numbers, so we have not really any complexity here with the physics, the turbulence, not modeling turbulence, so we can very easily model these physics with the PISO algorithm to couple the pressure and velocity fields. And open foam, I used the icofoam solver. It just happened to be the quickest one. It ran the fastest, and the results were not different between different solvers. So if we look at the comparison of the literature, I have highlighted or emboldened the experimental studies. There's not that many experimental studies, surprisingly. And mentioned by Triton, this 1959 guy, he said, or he observed that it was very difficult to get very accurate measurements on these force coefficients. So he recommends that people compare the Strahl number. Basically, it's easier to see the frequency of the shedding than it is to quantitatively determine the forces produced by that shedding. That's where CFD comes in, because it is easier to collect this data from CFD than it is from experiments. So if we look at the spread of data, the maximum error we see is less than 6%, and that is the experimental error that was already stated to be highly inaccurate relative to CFD simulations. Yeah. So looking at the single unconfined cylinder, the drag coefficient is plotted here. We see the oscillation in the drag coefficient. We see 10 seconds of non-dimensional time, and we observe as the mesh resolution is increased, we see this exponential convergence to a theoretical limiting value for an infinitely resolved mesh. And so I took a Richardson extrapolation of this data to compute a GCI from the ASME handbook, and the maximum GCI that I got from all of my data points, the Strahl number, the lift coefficient, the drag coefficient, the maximum was 1%. So the fine meshes that I'm using here are well resolved. So we can see here lift, and the RMS lift, the medium mesh and the fine mesh basically are overlaid on top of each other, although the fine mesh still is a little bit higher than the medium mesh's RMS value. And a power spectrum density of all the frequencies in this simulation are shown here. So we can see that the highest power spectrum density correlates to the most likely frequency mode. And so we see the frequency, the Strahl number, is slightly increasing for each mesh until we reach this value that was compared well with the literature values. So qualitatively, if we want to look at some pretty pictures, we can see that this is a good example of a cylinder. So if we look at the confined cylinder case, where we have those sidewalls, we see there is a lot less literature to compare to. So already, just by adding sidewalls, we're restricting the amount of literature available to compare. But we do have this one study by Sinha and Mahapatra. Sorry if I mispronounced that. But they provided the blockage values that I chose. I basically picked my blockage ratio based on the data points that they had for me to compare with. The highest error to any of these, none of this is validation, this is all verification because no one has done the experimental data collection for this case. But the verification error is around 5% maximum for this drag coefficient data point. Actually, I think it's this one, never mind. But maximum was 5%. So continuing, we're looking at the RMS lift coefficient, which compares tighter. There's a tighter spread around the values, which is interesting. It might suggest that the drag coefficient is the hardest to nail down, but that is to be determined by a future study. And the Strahl number, which is, again, the most important, probably the most consistent between different analyses to compare. We see decent comparison, and so this is good and makes me happy. And if I plot the pretty pictures, I'm still happy because they look good. And something to point out is that these, so if we also, I forgot to mention that this is a full shedding cycle, and so this is the first time step. Directly to the right is the quarter of the full cycle, this is half of the full cycle, and this is the full cycle. We can see that the vortices end up a little bit above the center line, and this is well demonstrated in the literature, and so the fact that I'm seeing this effect is good and gives me confidence that I'm simulating this correctly. So if we look at the tandem unconfined, again, where there's no wall but two cylinders, you can see the error range from all of the literature. The highest error is 14%, which is much higher than the error for the single unconfined case. This just means that either I didn't mesh this one as well. It's slightly different geometry, and I might have meshed it worse with the software that I was using, or it's just that the physics are harder to capture here, likely due to this region in between the cylinders. So the spacing here is 4 diameters, the pitch is 4 diameters, and this is a critical pitch because if you see, there's just enough space for a vortex to roll up behind the first cylinder until it impinges on the second cylinder. And so this spacing, again, since it's like a critical spacing in the literature, might be the source of that error between the literature, because I'm right here in the sensitive region, which maybe I shouldn't have put myself there, but I chose it anyway. So again, that was my basically building up my confidence in my model. So now I can go add the 2 cylinders and the sidewalls together, see what happens basically. So what happens is actually pretty interesting in my opinion. So this 0.1 blockage ratio would be the smallest cylinders, and this 0.25 blockage ratio would be the biggest cylinders. So we can see that for some reason, whenever we increase the blockage ratio, there is the flow has a transition from the first cylinder, essentially there's a single body regime until a certain blockage, and then it initiates shedding from both bodies. So originally, only the second cylinder is shedding, and then as the walls are brought closer, or the cylinders are increased in diameter, those are synonymous, the mode of the flow changes, and it becomes, instead of a single body shedding, each individual cylinder begins shedding, and we see that the drag coefficient begins to, this is easier explained with the pictures, and more intuitive with the lift coefficient. So the first cylinder has 0 RMS lift, or there's no oscillation there, there's no lift being produced by the first cylinder. This is symbolic of it being in a single body regime, so that only the back cylinder is oscillating and only the back cylinder has lift associated with it. But as we increase the blockage, both of the cylinders begin to shed, and both of the cylinders have lift. The Straw number is the same for both cylinders. I forgot to mention, they're kind of linked, they're hydraulically linked, so that the shedding of the first cylinder frequency should be the shedding of the second cylinder frequency. Yeah, and so this Straw number, although not associated with the front cylinder, obviously because it's not shedding anything, it's still associated with the oscillation in the lift for the back cylinder. And if we look at contours, this is for both cylinders, so this is the highest blockage ratio, or the biggest cylinders, or the closest walls, however you want to think about it. And this creates a very vigorous shedding. The vorticities and the magnitudes of the lift and drag are much higher for this case than in any of the other cases. And this is interesting because I didn't expect that to happen. I also didn't expect when the walls, when the blockage is increased, it becomes more likely to shed off both cylinders. It was just a more unintuitive solution. And so, yeah, I find it interesting. So it could be resonant geometry, where if you have the cylinders, again, spaced at this critical distance, and the wall spaced at this critical height, or critical channel width, I guess, it could initiate very strong lift and drag forces, which might be useful for something, I don't know. So my conclusions from this work are, this circle should not be right there, this circle should be right here. I don't know what happened. We need more experiments, basically. So all of this work, from the single confined cylinder to the tandem unconfined cylinder, there's essentially no experimental analysis. We're kind of blind, we're in the dark, we don't know what we should be getting, we don't know the correct real results. And so it would be nice to have more experimental analysis, especially in this region. Again, this is the one experimental comparison. They didn't collect any data like about their Straw number or their force and the forces, but they do show the shedding or the modes of flow. Again, this single body regime where the first cylinder isn't shedding cylinders, only the second cylinder is in blue, the blue triangles. And so we see in this region, my 150 Reynolds number at my 4 diameter pitch, there's a very, it changes flow modes in that region a lot. And so it would be nice to kind of expand that region, really figure out what's happening here. And if the very high force coefficients are observed by other people and not just me, that would be good to know. So yeah, that's basically the result and conclusion from my work. Here are references that I used. And do I have any questions? Any questions for the presenter? No question?
I have one question.
Yes. Yes.
Very interesting work, very impressive.
Thank you.
So I think the distance between the vortices when the vortex shading is occurring. I guess you can specify it as some lambda, right? Some wavelength essentially.
You're talking about the vortex size?
The vortex distance between two vortices.
Oh, the distance between two vortices. I need to
Right.
figure out how to do that.
So typically people write it as, if you consider the distance between two vortices as lambda,
Like this.
this lambda by d is a function of Reynolds number, right?
Okay, yeah.
So I don't know, for a single cylinder, if you plot this lambda by d as a function of Reynolds number, have you plotted how that looks like? Because you already have that data, right?
Yeah, no, I haven't looked at that, but that's interesting. to think about.
And then one could do similar plots of lambda by d as a function of Reynolds number, where two cylinders are present. And then now you can have a series of graphs where the distance between the two cylinders divided by d, and you can have a series of graphs, and you can see how, as that, let's say y by d, y being the distance between the two cylinders, how those trends change. So in one non-dimensional graph, you could probably capture the whole behavior.
Okay, that's good.
Right? That would be one way to represent the data essentially.
Yeah, that'd be interesting to show. Because it was rough for me to write this paper with the page limit, because I was like, I don't know, I got a lot of different cases and stuff to show, but thank you for the recommendation.
Because the
nice.
resonance should probably come out very beautifully.
Yeah, yeah, that'd be.
Plot it like that graph essentially.
Okay, yeah. Thank you.
Nice.
Yes.
Mostly just a comment, because you had observed higher GCI when you have the two contours, when you have the two cylinders next to each other, and it's like you've refined the mesh near both the cylinders, but in that intermediate region, things go from like fine to coarse to fine, and it could be a phenomena where what's happening downstream isn't adequately being captured past the first cylinder, which is causing some problems to propagate into what happens on the second cylinder. So in terms of refining, if I was going to do refinement, I would investigate what happens when you add refinement in between.
Yeah. Now with the things that I've learned in the past couple of years, I feel like I'd be able to recreate this mesh better and better capture these effects. But yeah, I agree with you. Any other questions?
One more suggestion, there is a grid generation scheme out there using partial differential equations. And the grids then start to look more like your streamlines. And then your numerical diffusion is typically less.
Okay.
So
that'd be interesting.
So yeah, there are grid generation strategies where instead of manually trying to grid to the grid, you can use partial differential equations to generate the grid for you.
Okay. Thank you.
I think Thompson's book actually was the first one that talked about how to